So, this lesson explores the idea of velocity in two dimensions. And quite like velocity in one dimension, it is a vector in two dimensions as well. With the only difference that now, in addition to x component, it has a y component also. And here, the x component and y component of velocity are completely independent of each other. What the object does horizontally has absolutely no effect on what it does vertically. They run on completely separate tracks that never interact. This is not just a mathematical convenience. It is a physical fact, and it is what makes every 2D motion problem solvable. Let me show you what I mean with a thought experiment that you have probably seen in a different form before, the bug on the wall. Imagine a bug crawling on a wall, tracing a curved path. At some particular moment, its velocity is pointing diagonally, let's say upward and to the right. That velocity vector has a horizontal component, Vx, and a vertical component, Vy. Now, imagine we switch off Vy entirely, as if we have a button that can disable the bug from moving in y direction. This means the bug would move only horizontally, in a straight line to the right. Now imagine instead we switch off Vx. The bug would move only vertically, straight up. So think and imagine. It's precisely because the bug has both components simultaneously that it traces the curved path. The curve you see is the result of two completely independent straight line motions happening at the same time. And one more thing to notice. The velocity vector at any point is always directed along the tangent to the path at that point. That's the direction of the velocity vector. So draw the curve, draw the tangent line at any point. That tangent line is the velocity direction at that moment. So how do we calculate velocity in 2D? Well, quite the way we do in 1D. That is, average velocity is displacement divided by time. However, here it is computed component by component. That is, v bar x equals delta x over delta t, v bar y equals delta y over delta t. Let's try one example. An object has delta x equals 12 meters and delta y equals 9 meters over a time interval of 3 seconds. Then v bar x equals 12 divided by 3 equals 4 meters per second. V bar y equals 9 divided by 3 equals 3 meters per second. And the magnitude of average velocity will be v bar equals square root of 4 squared plus 3 squared equals 5 meters per second. And direction, theta, equals tan inverse of 3 over 4, which is approximately 36.9 degrees above the positive x-axis. And remember, the direction of the average velocity vector is identical to the direction of the displacement vector since delta t is a positive scalar. That is, all you're doing is dividing the displacement vector by a number. Notice, positive x component, positive y component. We're in the first quadrant, so 36.9 degrees is correct as is. No quadrant correction needed. But always check, because you have already seen in the previous lesson how tan inverse can mislead you if the components are in other quadrants. Now let us understand the idea of instantaneous velocity in 2D. Well, in one dimension, you learned that instantaneous velocity is the slope of the position versus time graph at any given moment. That exact idea carries forward into two dimensions, but one direction at a time. Let's use our bug to make this concrete. The bug is tracing this curved path on the xy plane. At point A, right here, we want its instantaneous velocity. The direction is easy. Draw a tangent pointing in the direction the bug is heading. That's the velocity direction. Now for the magnitude and components. At the moment the bug is at point A, look at the xt graph for the bug's motion. The slope at time t when the bug is at A gives Vx equals 3 meters per second. In the same way, look at the yt graph. The slope there gives Vy equals 4 meters per second. Then magnitude, v, equals square root of 3 squared plus 4 squared equals 5 meters per second. And direction, theta, equals tan inverse of 4 over 3, which is approximately 53.1 degrees above the positive x-axis. So if you have a graph of x versus time, the slope at any point gives you Vx at that moment. If you have a graph of y versus time, the slope there gives you Vy. Read both slopes, apply the Pythagorean theorem and inverse tangent, and you have the full instantaneous velocity vector, magnitude and direction. So remember, the only quantity that links the x and y directions is time. At any given moment, the x motion and the y motion are happening simultaneously. So if you solve for the time something takes in one direction, that same time applies in the other direction as well. Time is the bridge that connects the two independent analyses.